Hello, this is EE637 and I'm Charles Bouman, and today we're going to do edge detection, but we're running a little behind, so I think what I'm going to do is go through this material at a brisk pace, okay? We've already kind of, I think, covered a lot of the edge detection concepts when we were covering other topics like filtering, so hopefully that we should be able to hit this pretty quickly. And the last time I just mentioned really briefly about the trade-off in edge detection, if we can, between false alarms and missed detections, and that's a really fundamental trade-off, and we'll be talking about that later when we talk about training. For minimum mean square error filtering of images. Hold on for a second. Yeah. Right. So, so that was a good topic to quickly cover, and I think some of this we've already covered. Really, I covered it earlier when we were talking about filters. So, but I'll say it again. That one thing is that, a feature which is very useful when you're trying to do edge detection is the local gradient. Edges usually represent some sort of physical phenomena, like an occlusion between objects in an image. So different images formed by different forms of sensing modalities have different properties. But in optical images, light doesn't generally pass through most materials. Obviously, certain materials like glass it does, clear glass, but it typically doesn't pass through the materials, and if it does pass through them, it scatters so that effectively it appears that they're opaque. So along boundaries, including boundaries of objects, you get discontinuous levels of intensity. And you can use those discontinuous levels of intensity to find those boundaries. So the gradient is very useful. But the gradient is a vector, so you can take its magnitude and its angle, and they each have a particular value. So a typical way to detect edges is to look for places where the gradient's above a threshold. The problem is if you put the threshold too high, you have too many missed detections. If you put it too low, you have too many false alarms. So now there are different ways of computing gradients, and I'm not really going into some of the details on this. Unfortunately, maybe it would be better if this was a 2-semester course. I don't know if it would be better for you, but I don't know. But in any case, given the constraints we have, there's like a very classic edge detector that's pretty effective is the so-called canny edge detector, but we won't have time to go into that. But these are different ways you can compute gradients and in order to be able to detect edges. And one of the problems that comes up is that there's sort of a trade-off, because if you take the differences between two adjacent pixels, essentially what happens is your measurement of the gradient is off center, because you're really measuring the gradient effectively at that point right there, right? Yet the value has to be stored somewhere, and typically where it's stored is at that position right there. So your gradient estimates will be systematically shifted. And what's actually even more problematic is that your derivative along the x direction is going to be shifted a half a pixel to the right, and your derivative along the y direction is a half a pixel down, so that they're not aligned anymore, and that can be a problem. So one possibility is you can do this. You can take the gradients along the diagonals, and then at least the two gradient derivatives centers will be aligned. But often what's done is you do something like this, because where you use a little bit bigger window, and then the advantage of that is that you also can put a little bit of filtering in. So here you're smoothing along the y direction because you're computing the derivative along the x. So there's obviously trade-off between accuracy and localization and noise suppression, because whenever you're taking a derivative, you're going to tend to enhance noise, and that's a problem. And that'll increase the false alarm rate and the misdetection rate. Okay, so you can play around with these various things, and then there's an edge thinning issue, which is that if you set a threshold in the gradient, what'll happen is you'll typically, if you set the threshold low, you'll get a thick edge. If you set the threshold high, you may get a thin edge, or you may get no edge at all if it's too high. So a threshold which is appropriate for detecting edges, giving you a good trade-off from edges, it generally will tend to produce too thick an edge in different locations. So there's a few ways around that. One way is that you can actually try to localize the position of the edge along the line more accurately. So you can find a direction along the gradient that's maximum. It maximizes the gradient, and then along that line you can search for a maximum of the gradient, or you can just find the center pixel. Finding the maximum is probably the best thing. But a very commonly used technique, which we discussed earlier, is to look for the zero of the second derivative. Excuse me? Oh, you have a question?
So in this way, when we set a threshold, the caveat is that what if we have that threshold, we have two peaks?
Well, okay, so what can happen is that, so if you have, so let's say this is the image, right? And you have something like this. Right, and then you measure the gradient of the magnitude of the gradient, say. So what you'll get is something like this. Say, well, let's say it's a broader peak than this. So if you set a threshold, you'll get two peaks. And that's good because there's two edges. But the other thing that'll happen is that if you set the threshold low like this, you'll get a broad peak. So when you do the detection, you'll get a broad peak like this. So the edge will be thick. And in a lot of applications, you want a more precise specification of where that edge is. You know, one thing that comes up in images is that often you'll say, well, oh gosh, you know, why is it that important that I get the position of the edge that accurately? Or why is it important that the resolution of the image be that high or something? Well, if you know, inevitably these things come down to cost, and if you lose, if you only get the precision of the edge, if you're off by a factor of say 4 in the precision of the localization of the edge, or 2, then in 2 dimensions that's a factor of 16, 4 times 4. So you could have reduced the resolution of your sensor by a factor of 16. A factor of 16 is usually a fair amount of cost in the sensor design. So either you could have used a much less expensive sensor, right, or you could have gotten a much better answer. Okay, so you know, it's intuitively obvious, I think, to people when they go shop for things that a 16 megapixel sensor is better than a 1 megapixel sensor. But sometimes it's not so intuitively obvious that by doubling the resolution that's really important. Okay, so, or you know, so yeah, so it's a to use a bad analogy, imaging is a game of inches or pixels, maybe I'd say, a game of pixels, right? You know, being off by a factor of 2 is a lot. It's huge, and in 4 dimensions, 2 to the third power is 8, right? 4 to the third power is 64. So, you know, these are huge factors. Okay, so now, so how do you localize the precise top of that peak, right? Well, everybody knows that when you want to solve an optimization problem, you take the derivative. So this is f of x, right? This is the derivative, so this is f prime of x, say absolute value. And then the derivative of that is going to be f double prime of x. So you take the second derivative and you set it equal to 0. And that's how you find the peak. So in 2 dimensions, what people typically, so this just shows, this is a diagram. It shows that, okay, you have an edge. You take the derivative. You want to find the peak. If you just set a threshold here, you'd have too broad an edge. So what you do is also take the derivative of this and set it equal to 0. So, so basically, what you do is you have 2 criteria. You have the criteria that you have the criteria that the second derivative is 0, and the criteria that the first derivative is greater than the threshold. If you only have the criteria that the second derivative is 0, then you're going to get a lot of false alarms for edges in places where it's not very edgy, right? So, for instance, if you have, if you had something like this, and you just had like something like this, right? So, the first derivative is going to be something like, it's just a little tiny peak there, right? And then the second derivative, well, it's just going to go like this. It's going to meander around, and you're going to get false alarms every time you hit 0. So that's not robust. But the combination of the two conditions is that you want the second derivative to be 0 and the first derivative to be above some threshold. And then that gives you a peak at the position of the maximum, right? Okay, so I talked about how you can compute the second derivative. I did this before when we were talking about filters, so I won't do it again. But basically, if you numerically calculate the second derivative, you find that the second derivative operator has the form of taking the pixel, subtracting the average of its neighbors, and multiplying by -2. So usually what happens is you just take a pixel and subtract the average of its neighbors. This is like the unsharp mask. So the unsharp mask times -2 is the Laplacian. But you're setting, it's the second derivative. But you're setting that equal to 0 anyway, so the fact that you multiply by -2 is not so important. You can either set the second derivative equal to 0, or you can set -2 times the second derivative is equal to 0. It's the same thing. So basically, you're looking at points where f of n minus 1/2 f of n minus 1 minus f of n plus 1 equals 0. Now, there's a practical problem with this situation, which is that if you define this thing as, say, g of n is never going to actually be equal to 0. Because it's a discrete signal, with high probability, it won't actually come out exactly to 0 in too many locations, right? So what you really need to do is look for places where g of n sign changes. Because any place that sign changes means that it went through a 0. So you look for sign changes. I think it would be great if we had space to add one more lab on edge detection, but you guys probably wouldn't enjoy that. I can dream. Yeah, any questions?
So in this case, it doesn't matter if it is non-causal, because we have the...
That's right. Causality... Causality has very strong implications when you're doing real-time processing of a system. So you have x of n as the input and y of n as the output, right? And this is like a filter in your iPod. Or, no, iPods. I guess, I don't know, maybe that's passé now. I guess now it's iPhones, okay? It's i-something. In your iX, okay? This is a filter in your iX, okay? And... you know what? When this becomes really popular, IXs, when everybody's talking about IXs, you can attribute it to me, okay? Okay, and I'll take patent royalties on that too, okay? Or copyright anyway. But when you put this filter in your IX, you got to get out. It's got to be a causal filter. It's a streaming signal, okay? So you have no choice. But when you have an image, the concept of causality is not so clear, right? You've got an image here, and you're going to produce another image here, and if you can afford to buffer it in memory, you don't care about the latency of one frame, okay? Then you're not really constrained to what causal filters, because there is no real concept of causality, right? This pixel goes to here, and you're going to do a lab, okay? After the color imagery lab on image restoration. Okay. And the image restoration lab, that'll drive that home. Okay? So yes, it does not have to be causal. In fact, the whole concept of causality for images is unnatural, okay? And as is often the case, the little glitches that occur in these problems can spawn off entire research field and keep armies of academics employed for years. It's a wonderful thing, okay? But I told you that scaling, the fact that scaling doesn't work in discrete time, has, like, created entire fields of multi-rate filtering. And also wavelets. Okay, and the fact that causality is broken in 2D. That's generated entire fields of things called like Markov random fields, and all kinds of things. Markov random fields, what they call loopy models, and what some they call excuse me. Well, that's not necessarily non-causal. There's another word I'm looking for, and I'm just not. Sometimes they call graphical models. Okay, that was the term I was looking for. So it keeps us employed. It's good. Otherwise, we'd get in trouble hanging out in the park and stuff like that. It keeps us busy. So, okay. So the basic idea, when you generalize this to 2Ds, there's actually more than one way of doing it. But the common way of doing it is that the natural generalization of the second derivative in 2D is Laplacian. It's the gradient of the divergence of the gradient. And it turns out to be just the second derivative along the x-axis plus the second derivative along the y-axis. So if both those things are equal to 0, you say that the function is at a local maximum. That's not really totally true. Okay, okay. There's actually more precise generalizations of this, but this is what actually people mostly do. Okay, but in that case, it's the same sort of thing where you subtract the signal from the average of its neighbors. So you take so Laplacian. So I guess the Laplacian of f is equal to, I think it's -4, okay, times f of n minus 1/4 times f of, I guess I got to make this 2 dimensions, f of mn, f of mn plus 1 plus f of mn minus 1 plus f of m plus 1n plus f of m minus 1n. So this is the average of its neighbors. That's an f. Okay? So you take the pixel minus the average of its neighbors, and that's proportional to the Laplacian. So this is what you want to be equal to 0. Okay? It's pretty simple. Fine. And I think that's pretty much. So to do edge detection, you set the Laplacian to 0, and you check to see that the gradient, the magnitude of the gradient is greater than some threshold. Now, when you compute the magnitude of the gradient, this requires a square root, because you have to take the square of each component of the gradient and take the square root. But you can simplify that expression by just taking the magnitude of f squared. Okay, in that case, that's going to be equal to like df dx squared plus df dy squared, and then you can compare that to t squared, and that removes the need to do a square root, which is sometimes a problem because square roots are slow on a lot of computers, right? Okay, so all right, good. Now you guys did the connected components lab already, right? So you already know all about this. So I can briskly run through this also, right? How many people finished the connected components lab? Oh, great. And let me actually start off with, were there questions about it? Did people feel like they understood it? It was a little challenging probably, but in the end, it makes sense, right? Okay, so connected components, there's a few reasons I teach connected components. One is that they're really useful in a lot of applications. So it's just a handy piece of code to have around, right? I always tell students that, particularly undergraduate students, that when they take a course and they have a textbook, the students it's like there's been an evil plot by society to convince students that they should sell their books back, okay? This is like a horrible idea, because once you put all that time into understanding a book, that book is infinitely more valuable to you than it is to anybody else. If you keep it, you have this wonderful reference that you understand. And it's a similar thing with code. Once you've written a piece of code, you really understand the piece of code you've written. It's like very useful. You can customize it and reuse it. So I find that students who do the connected component analysis, they benefit a lot from having had that experience, because it's a standard piece of code. It comes up in lots of applications. But the other thing is that it's useful because it's an example of sort of a generic type of segmentation, which is called region growing. There's basically a few different ways you can go about segmenting images. One is to one is to take individual pixels and try to classify them based upon their attributes, okay? And the other is to look for basically edges in the image, places of discontinuity, separation, something that's changed between pixels. So in one case you're looking for change, and the other you're looking for absolute behavior. And of course you can combine the two. You can have methods which the combined attributes of looking for some kind of like homogeneous behavior and also looking for some change in behavior, okay? But region growing methods and connected component analysis are looking for some sort of change, okay? And methods that look for change tend to have a certain sort of common structure in the way they're organized, okay, from an algorithmic point of view. So connected components is a great way of illustrating that. And the idea in connected components is that you want to segment an image into different regions using, say, a 4-point or an 8-point neighborhood or any neighborhood you want. And the idea is that you first define some criteria. So So C of S here is the set of neighbors that are connected to the pixel S, okay? So now, C of S could be some monstrously complicated function, right? It could, appeal to some hideously complex oracle, right? It could be like involving computer vision and everything else, right? So you have some complex scene, and you're asking whether two pixels are neighbors or not. It might be that, well, you have to, so it could be that this is your scene, okay? And you have, like, part of the scene involves happiness, okay? And the other part of the scene involves despair, okay? And you have to so two pixels are connected if they're both happy, okay? So it might require enormously complex analysis of the scene. You'd have to interpret the scene, understand what's going on, try to, infer the emotional feelings of the participants in the scene. It could be very complex, okay? Okay? But and that's the beauty of mathematics, because you can just write this little equation down. You can say, yeah, but if they're the same, C of S is equal to 1, and otherwise it's equal to 0, okay? So the beauty of mathematics is that you can basically distill enormously complex and intractable processes into a little simple function like that, okay? And it's a beautiful way of deferring the difficult problems to the future, but it allows you to make a lot of progress. So this framework can handle a lot of complicated scenarios, okay, is my main point. But once you have this function, now what you can do is you need to try to find all the pixels that have some sort of common behavior, okay? I know you've already done this lab, so I'm going to make a point, which I think is an important one, maybe you want to reflect upon. In the particular, there's a distinction between connected components analysis and just classification. So let's say you have an image, right? And each pixel in the image is classified as the image contains ones and zeros, okay? So you might have a region here of ones, and you might have a region here of ones, okay? And you might have here a region of ones, and the rest of it's all zeros, okay? These are all zeros. Those circles are not to be confused with regions, okay? Maybe I'll put little lines through them to make them look like zeros, okay? Now they look like null sets. But anyway, okay, so what can I tell you? I did my best. Okay, so these are regions of ones, okay? Now, the thing is that's fine. So now every pixel is classified as 1 or 0, but often with connected components analysis, I'll put here CCA, connected components analysis, you don't just want to know whether the pixel is a 1 or a 0, you want connected sets of ones. So you need to take each of these regions and reclassify it basically as a single grouping, as a single entity, okay? So this will say all the background remains 0. That's all connected. This guy here is going to go to 1. This guy here is going to go to 2. And this guy goes to 3 because they represent 3 different things. Okay? And you say, well, what do you mean they represent? Well, it depends on your application. But there's a lot of cases where you may want to do this. A classic example where this comes up a lot is if you have a document. And you take the document, you scan it, and you threshold it, and the text is black and the background is white. So each character shows up as a black pixel. You threshold it, and when you threshold it, now each character is a different, is one. But you don't just want to know whether a pixel is a character pixel or a background pixel. You also want to separate it into the different characters or the different symbols. So each one needs to be a different connected component. Okay? So that's one function of connected component analysis. The other is what you did in the lab, where you have an image, and it's a continuous image, and there's some gradations, and there you have some sort of threshold, and you want the pixels that are less than some threshold to be viewed as being the same. So this is almost like a form of edge detection. Okay? Now, I should warn you that this is not the grand solution to all segmentation problems. Okay? It's a nice framework in which all kinds of segmentation problems can be formulated, but it is not the grand solution, because what can happen, the flaw in this approach is that you have some image, and you may have seen this, okay, in your application. You have some image, and let's say the image is, I don't know, it's got to be a dog, okay, and this is going to be a great challenge for me. Okay, so this is a dog. Oh wow, I'm doing well. Okay, let me see how well I do. Okay, that's a dog.
Don't quit your day job.
You don't quit my day job, for sure. Okay? Okay, there we go. There's a dog. Okay? Oh, God, that's bad. Okay, there's a mouth. Okay, anyway. I can't even remember what I was doing. Okay. So there's a dog. Okay, now the problem is, now what happens if it turns out that, okay, the background of the dog, here's a tree, okay? Dog. And let's say the dog has brown fur and the tree has brown bark, okay? And what happens is this. So, at this pixel right here, the color of brown is almost the same. What's going to happen? It's going to leak through and go, okay? And all of a sudden, the dog and the tree are going to get mixed together. So the problem is it's not robust, because one pixel can ruin your entire day, okay? So that's a problem. Now, you can try to do things. You could try to smooth the image. In this case, smoothing won't necessarily help. You could try to extend the edges. You could try to use higher level information, but in the end, there tends to be a natural non-robustness to these methods. But the advantage of them is that they exploit a lot of useful information. So So it's a challenge, and there's no universal solution to these problems, okay? So I'm not going to go through the, I mean, I think at this point, I heard a lot of you complaining that you were being tortured by trying to write this program, but I've heard that, I don't hear people complaining anymore. So I've been figuring that they must have figured it out, okay? Did they get it? Has anybody not been able to get this program to run yet? If not, you should definitely talk to Jordan, because he's really good at helping with this sort of thing, or a friend or something. But basically, the idea in this method is that okay, you start off by you initialize y sub r is the image and where you keep all the labels. So each pixel is going to be labeled as to its class, okay? So you start off by every pixel being labeled 0. So that indicates to you that the pixel is not yet labeled, okay? Okay, now what you do is you call this function connected set, and you try to find every pixel which is connected to this is the seed pixel, S0. So you first of all, B is a set that you maintain, and you keep doing this until B is empty. You start off by initializing B with S0, okay? And then while B is not empty, okay, what you do is here, first you pick any element of B, and you put it in S. Then you remove that element from B, because you've taken it out. Right? Now what you do is you label S with the class label. Oh, class label is the thing you passed. You're going to label every pixel. Certainly, you're starting with S0, so certainly S0 is going to get labeled. S0 is in B, so every pixel in B is going to eventually get labeled. Okay, so now what you do, and this is the tricky step right here, okay? You say, okay, I'll take B, and I'm going to add to it any pixel which is connected to S, from those pixels, I will remove the ones that have been previously labeled. If it's already been labeled, I don't want to do it again. Otherwise, I'll just keep going around in circles. So what I do is I take all the pixels that are connected to S that have not yet been labeled. All right? And if they've not yet been labeled, if their label is 0, because that's the unlabeled pixels. So these are all the pixels that are neighbors of S that have not yet been labeled, and I add them back to B, and then I repeat, okay? Now, here is an example. We're going to run connected components on this, and the connected components here, this is one connected component here. This is another connected component. This is going to be a third, and that's a fourth. And we start off with this guy. So that guy's location is 0, 0. So we add 0, 0 to the set B. Okay. Then we find, okay, so when 0, 0 is added, now we find it's all the neighbors which have not yet been labeled. Well, that's not a label. That's not a neighbor of that because they're different. They're different values. This one is a neighbor. We're using a 4-point neighborhood, I believe. Yeah, this is a neighborhood. This is a neighbor. It is the same value, so that one gets added, and its index is 1, 0. So 1, 0 gets added. 0, 0 gets removed. Okay. Okay. Now, once we have 1, 1, this guy's already been added, so it's already a 1. So we ignore it. Anything that's already, the way I like to think of this is it's like, I'm trying to think, what would it be like? It's like you have it's like you have bacteria in a petri dish, right? And the bacteria grows, okay, until it uses up all the food locally, right? So you put like a little bacteria here, right? And maybe you distributed some food in some pattern. So the bacteria grows, but once it's used up all the food, it dies. So the wave sort of spreads out, right? And if this is the shape of the food, it spreads out until it's used up all this, and then it sort of goes forward. You can almost like think of it like this: if you put some flammable kind of explosive material, thin film over here, right? And then you lit it, it will, right, and burn out. Okay, that's the same sort of underlying phenomena that occurs with this region growing. Okay, so now that neighbor here is connected, so it gets added. It's 1, 1. Let's see what's next. Blah, 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 blah. Okay, here we got 2, 1. 2, 1, that's a 1. Okay, so its neighbor is here and here, so it's got 2 neighbors next. That's going to be 3, 1 and 2, 2. 3, 1 and 2, 2, and here they are, you see? I was actually right. There's 3, 1 and 2, 2. And it keeps growing out until it's grown out all the way, all right? And now what happens is you just start pulling things off the stack. If you look at 4, 1, 4, 1, it doesn't have any neighbors which are of the same type and unlabeled. So it just gets thrown away. And then you look at 3, 2, 3, 2, and same deal. So there's nothing to add. Oh. Right, 3, 2, there's nothing to add. So it gets removed. And then 2, 2, there's nothing to add there. So you're done. The stack is empty, and you've labeled that region with 1s. Now you continue on, and you do the next region. Okay, so first you initialize with 0, 0 with 1s. Okay, so that's what we just showed. Then you do 0, 1, and you label it with 2s. So the connected things that grow out of here all fall into here. It's almost like a water filling algorithm. There actually is something called a watershed algorithm, which is different. And it fills in here. Now what's going to happen is you're going to raster through until you get to that point right there. That's going to be the next point where anything happens. That's 2, 0. And when you get to 2, 0, 2, 0, you're going to label with 3s, so that gets all filled in with 3s. And now that's the only point that hasn't been labeled. So you'll keep going through until you get to that point, and then you'll label that with a 4. Okay? Good. So now you're all experts on connected components. Let's see. Okay, now, segmentation. There's 2 fundamental methods for segmentation. One is merging. Okay, this is region-based segmentation. In region growing, we were really looking for edges. In region-based segmentation, there's 2 fundamental approaches. One is merging, and the other is splitting. I mean, this is true for any what's called clustering problem. Clustering comes up a lot in applications in imaging, and it's a fundamental technique in what's called pattern recognition, or more recently it's called machine learning, or statistical learning. So what happens is that humans are very good at this sort of thing. If you have some sort of data, so let's say you have an aerial photograph, and you see a bunch of people, and they're standing here, and you see another bunch of people there, right? Right? People will just look at that and they'll say, well, there's 3 groups of people. It must be 3 groups of people that are talking to each other. But a computer has a lot more difficulty making that simple inference. Mm-hmm. So how do you look at this and infer that? The computer might think, well, there's 1 group of people, but you'd say, well, hold on, come on, they're really close together, and much further than they are. So how do you do this? There's 2 fundamental ways of doing clustering. And when you do clustering spatially, it's essentially segmentation. But there's 2 fundamental ways of doing clustering. One is to cluster agglomeratively, which means to merge together things that are similar. And the other is to cluster divisively, which is to separate things apart that are dissimilar. Okay, so the advantages of so there's agglomerative clustering, which is bottom up, and there's divisive clustering, which is top down. Okay, you know what? This is really fundamental. I mean, forget about electrical engineering. This is life. Okay, I mean, in life, there are two basic approaches. Okay, one is top down, and the other one's bottom up. It's true in government. It's true in organizations. It's true in just about anything you can imagine, okay? And neither method is perfect, okay? Both methods have advantages and both methods have disadvantages, and most practical solutions combine the two approaches. They're really two extreme solutions, okay? But practically, now very often you'll use just one of these two, okay, because it's simpler. But usually an optimal approach really combines the two. You can usually do better by combining the two. Okay, do a little bit of top down, do a little bit of bottom up. Okay, and maybe go back and forth a little bit. Okay, so the advantages of bottom up is that it tends to be better. It tends to produce a better result. Okay, but the disadvantage of it is that it tends to be very expensive and complex. Okay, because if you have n things, if you have n people, and you want to do a bottom-up clustering, to do n people, you have to look at all their interactions, n squared. So you have to say, this is Bob here, okay? You have to say, Bob, how do you like Ali here and Sarah there? And you go, well, you know, Sarah's okay. I really like Trudy better, or something like this, okay? And it gets very complicated. And you ask Trudy, you say, well, I don't really like Bob very much, okay? So you're going back and forth, and you negotiate, and oh my gosh, and you know, okay, can we schedule 2 more meetings for next week? Okay? So by the time you're finished, you've wasted a huge amount of time, but you do get a good result if you can persevere through, okay? Now the alternative approach is divisive clustering, where what happens is Greg, the CEO here, comes in and says, okay guys, we're going to do this, okay? And Trudy goes, hold on, I was with these people over here. And I go, I don't care. Just move your office, okay, over here, and we're going to get this done, okay? So, you know, but the advantage is it gets done fast, okay? It may not be perfect. Then you can fix it up later. Like when you do another reorg next year, you can get Trudy back with their colleagues or whatever, okay? So you have top down and you have bottom up, and that's basically the upshot on that. Now, hold on. Okay. Now, when you're doing this sort of thing, it's always nice, but not always possible, if you can summarize all the information necessary to make decisions about merging and splitting. Oh, and I should say, okay. Oh yeah, and then split and merge. I should have mentioned this. Okay, so a simple way to combine top-down and bottom-up approaches is that what you can do is you can first split things, okay, and then once you've split it as well as you can, remerge and then split again. So you can go back and forth, and you know, it's a nice heuristic that's pretty effective. Okay. Now, if every time you need to make a decision about whether to merge or to split 2 groups in the clustering, you have to go back and look at all the original data, then that's a huge amount of extra computation. You'd like to be able to summarize most of what's important about the group in some abbreviated form. So often it's the case that you can actually extract what's called a feature vector. A feature vector is an incredibly powerful concept, okay? Let me see. Am I running out of paper? Oh, no. Oh, here we go. Oh, good. A feature vector is an incredibly powerful concept, okay? Whenever you're trying to make a decision about a system, okay, you start off like this. You say, okay, well, I have X, and X is just, you know, unbelievably complicated, okay? let's take something. It's the so your objective is to I don't know, decide which movie deserves the Academy Award, okay? Okay. So each X is all the information associated with a movie, okay? It's, it's 2 hours of video footage, it's the extra features, it's all the statistics and information and history of the actors and actresses, it's all the cultural news stories related to the thing, okay? It's enormous, it's gigabytes of information, many gigabytes, terabytes, petabytes, or whatever comes after a tera, I don't know. Femtobytes. No, that would be really small, I guess. But anyway, you take this guy and you put it into a box, okay? But it's very simple because this is f of x. And then what happens is that f of x is equal to 1 if it wins the Academy Award, and 0 if it doesn't, okay? So it's quite simple from that point of view. Unfortunately, f is now a very complicated function, okay? So what you could do then is you could say, okay, this designing this f becomes insurmountably complex. So instead, you have this idea where you say, okay, I'm going to take x, right? Let me make this another function. I should have made, well, okay, I'm conflating functions. Okay, I should have used, make this a g, okay? What I do is I take x and I put it into some function f of x. And from that, I generate a thing, I want to use consistent notation here. This becomes fk, okay? And fk is a member of R to some dimension, and I want to use the right letters here. R to the, I make that an n, and this is a k. This is a feature vector. So what you do is you summarize all the information in X with a relatively low dimensional feature vector. So K here could be, I don't know, it could be 10, it could be maybe 100, it might be 1,000, okay? But it's generally not like 10 to the 12, okay? So dealing with something that's a dimension 100 or maybe even 1,000, but hopefully 10, is a lot easier than dealing with something, X here lives in a space of 10 to the, 12. So now once you do that, you put this into G hat of Fk, and you use that to produce the decision. So you try to summarize this high-dimensional object with a much lower dimensional feature vector. Okay. Now, ideally, what can happen is that so feature vectors might include things like, if you're doing segmentation, it might include things like color. It could involve texture. Okay. It could involve aspects of morphology or shape, like if it's a region, it could contain information about the width or height of the region, or the relative adjacency, or boundary smoothness, all these kinds of things. The beauty of this framework is you lose something because now you no longer have access to all the information, but you've gained a lot of simplicity. So with this feature vector now, what you can do is you can decide when two regions are similar by deciding if their feature vectors are similar enough. So, and hopefully what can happen then is when you merge two regions that you can compute the feature vector without going back to the original regions. You can compute the feature vector as a function of the two feature vectors. That's not always the case. It's often not the case, but it's often an approximation you can make. Pick feature vectors which can be computed that way. So for example, and I'm running out of time, but I'm going to blaze through this, that if you pick the feature vectors being the number of pixels, the mean color, and the variance of the color, those are things that can be computed recursively. Okay? So I'm trying to get to, I think I'm going to try to pick up on the color material at the next lecture. So go through some of these notes yourself. I think this material is pretty self-explanatory, and we'll get the color next time. Thanks. Bye.